fact, it doesn't have even very basic software like Git. So if I were to type Git here, hi, I'm Lak. Welcome to the first module of our Big Data Fundamentals course. It provides an introduction to Google Cloud Platform. In this module, we'll examine the infrastructure behind Google Cloud Platform, or GCP, which was originally built to power Google's own applications and is now available to you. Then, we'll cover the big data and ML products that are built on top of that infrastructure and when you should choose which products for your solution architecture. After that, my favorite part of this course, learning from other customers who are using Google Cloud by exploring their use cases and getting inspired to solve similar challenges for your own teams and projects. You will learn where you can look up reference case studies of GCP customers by industry or by product. And then you'll examine their solution architecture in a short activity. Building the right team structure is critical to solving these big data challenges. We'll explore the different types of roles and personas for building a successful big data team within your organization. Consider for a second the impact that Google Search has on our daily lives with timely and relevant responses. Now think of other Google products: Gmail, Google Maps, Chrome, YouTube, Android, Play, Drive. Each of these products has over 1 billion monthly users. Google has had to develop the infrastructure to ingest, manage, and serve all the data from these applications, and to do so with a growing user base and data requirements that are constantly evolving. 7 products with 1 billion users. Actually, there's an 8th Google product that has 1 billion end users. Google Cloud, except that it's your users. The end users served by Google Cloud customers such as Home Depot and Spotify, Twitter and New York Times, Colgate-Palmolive and Gojek. Let's look at the building blocks behind Google's big data infrastructure and how you can leverage it with Google Cloud. There are 4 fundamental aspects of Google's core infrastructure and a top layer of products and services that you will interact with most often. The base layer that covers all of Google's applications, and therefore Google Cloud's too, is security. On top of that are compute, storage, and networking. These allow you to process, store, and deliver business-changing insights, data pipelines, and machine learning models. Finally, while running your big data applications on bare metal virtual machines is possible, Google has developed the top layer of big data and ML products to abstract away a lot of the hard work of managing and scaling that infrastructure for you. A growing data organization like yours will need lots of compute power to run big data jobs, especially as you design for the future so that you can outpace the growth in new users and data for the next decade. Let's start with an example illustrating how Google uses its own compute power. Google Photos has recently been introducing smart features like this one for automatic video stabilization, for when the camera is shaky, as you see here on the left. What data sources do you think are needed as inputs to the model? Well, you need the video data itself, which is essentially lots of individual images called frames ordered by timestamps. But we also need more contextual data than just the video itself, right? Absolutely. We need time series data on the camera's position and orientation from the onboard gyroscope and motion on the camera lens. So, how much video data are we talking about for the Google Photos ML model to compute and stabilize these videos? If you consider the total number of floating point values representing a single frame of high-res video, it's a product of the number of channel layers multiplied by the area of each layer, which with modern cameras can easily be in the millions. An 8 megapixel camera creates images of 8 million pixels each, approximately. Multiply that by 3 channel layers, and you get over 23 million data points per image frame. And there are 30 frames per second of video. And you can quickly see how a short video becomes over 1 billion data points to feed into the model. And from 2018 estimates, roughly 1.2 billion photos and videos are uploaded to the Google Photos service every day. That is 13 plus petabytes of photo data in total. For YouTube, which also has machine learning models for video stabilization and other models for automatically transcribing audio, you're looking at over 400 hours of video uploaded every minute. That's 60 petabytes every hour. But it's not just about the size of each video in pixels. The Google Photos team needed to develop, train, and serve a high-performing machine learning model on millions of videos to ensure that the model is accurate. That's the training dataset for this one feature. Just as your laptop hardware may not be powerful enough to process a big data job for your organization, a phone's hardware is not powerful enough to train sophisticated machine learning models. Google trains its production machine learning models on its vast network of data centers and then deploys smaller trained versions of these models to the hardware on your phone for predictions on new video. A common theme throughout this course is that when Google makes breakthroughs in AI research, it continues to invest in new ways to expose these as fully trained models for everyone. You can therefore leverage Google's AI research with pre-trained AI building blocks. For example, if you're a company producing movie trailers and quickly want to detect labels and objects in thousands of these movie trailers to build a movie recommendation system, you could use a Cloud Video Intelligence API. You could use that API instead of building and training your own custom model. There are other fully trained models for language and for conversation too. You will learn and practice using these AI building blocks later in this course. But getting back to the Google Photos machine learning story, running that many sophisticated ML models on large structured and unstructured datasets for Google's own products required a massive investment in computing power. That's why Wired says, this is what makes Google Google. Its physical network, its thousands of fiber miles, and those many thousands of servers that in aggregate add up to the mother of all clouds. In essence, Google has been doing distributed computing for over 10 years for its own applications, and now has made that compute power available to you through Google Cloud. But simply scaling the raw number of servers in Google's data centers isn't enough. Here's an interesting rough calculation by Jeff Dean, who leads Google's AI division. He realized years ago that if everybody wanted to use voice search on their phones and used it for only 3 minutes, we would need to double our computing power. Historically, compute problems like this could be addressed through Moore's law. Moore's law was a trend in computing hardware that described the rate at which computing power doubled. For years, computing power was growing so rapidly that you could simply wait for it to catch up to the size of your problem. Although computing power was growing rapidly even as recently as 8 years ago, in the past few years, growth has slowed dramatically as manufacturers run up against fundamental physics limits. Compute performance has hit a plateau. One solution is to limit the power consumption of a chip. And you can do that by building application-specific chips or ASICs. And one kind of application is machine learning. Google's designed new types of hardware specifically for machine learning. The Tensor Processing Unit, or TPU, is an ASIC specifically optimized for ML, and it has more memory and a faster processor for ML workloads than traditional CPUs or GPUs. Google has been working on the TPU for several years and has made it available to other businesses like yours through Google Cloud for really big and challenging machine learning problems. One such business that uses TPUs is eBay. They use cloud TPU pods to deliver faster inferences of predictions, faster inferences to their users by a factor of 10. That's a 10x speed up. The decrease in model training time has also led to faster model experimentation. ML model training and feature engineering is one of the most time-consuming parts of any machine learning project. eBay's VP of New Product Development remarked that the additional memory of the TPU pods enabled them to improve their turnaround time and iterate faster. One last example of compute power at Google and an inside look at our culture of thinking 10x is how our teams used machine learning to boost Google's own data center efficiency. The potential impact for machine learning was there, considering the number of data centers that Google has to keep cooled and powered, and we were already collecting streaming sensor data for our existing monitoring platforms. Engineers at Alphabet's DeepMind saw this as an opportunity to ingest that sensor data and train a machine learning model to optimize cooling better than existing systems could. The model they implemented reduced the cooling energy by 40% and boosted the overall power effectiveness by 15%. I find this example particularly inspirational because it's a machine learning model trained on machine learning specialized hardware in a data center, telling the data center how hot it can run the machine learning specialized that the model is training on. Powerful inception level stuff. Later in the course, you will see a demo on how you can set up a streaming data ingestion pipeline for your own IoT devices in less than an hour. It says Git is not found. So I need to install Git. Good thing is we can do that, right? I have root access. And so what I can do is I can do sudo, which gives me root access, apt-get install Git. Okay. And it says, do you want to continue? Yes, I do. And this now installs Git, which is a way to access my source code repository, which contains everything else that I need. So I will go ahead and do git clone, https www.github.com, Google Cloud Platform. So this now gets the data from GitHub, gets all of the data that I need, including the files. And now if I do ls, I have my repository. And in this case, This is part of the files for this course. And so we can go into BDML fundamentals, and there is the earthquake VM. I'll go into the earthquake VM and look at what files are present. Turns out that I have an HTML file already. I have some a shell script to ingest data. I can do less ingest.sh. And this basically goes ahead and removes an existing earthquakes.csv and does a wget, which is a way to download data over HTTP from earthquake.usgs.gov and saves it as earthquakes.csv. So that's what ingest.sh does. But in order, then I also have transform.py, and transform.py basically is some Python code that uses matplotlib to go ahead and parse the earthquake data from USGS and put it on an earth map, creates a PNG out of it. So this particular file can be run to go ahead and process a weekly data from the USGS. It goes ahead and gets 1 week of data from USGS and creates earthquakes.png. In order to do that, though, I need to have some software installed, and the software that I need, it's all listed in the installed missing.sh. So I need to basically get a bunch of different Python libraries. So let me go ahead and first run install missing.sh. This goes ahead and downloads and installs all of the Python packages that I need. As you can see, working with a virtual machine on the cloud is like working with any other Unix machine. In this case, because I created a Debian machine, I get a Unix machine, and that's the Unix machine that I'm working with. At this point, it has all the Python packages that I want. We can go ahead and say ingest.sh, and it will go ahead and download an earthquakes.csv. You can see that there's an earthquakes.csv now that's been created. And if we were to do head shows the first few lines of the file. It turns out that currently there has been an earthquake in California, and there has been another earthquake in Alaska, and so on, right? So let's go ahead. And so there's 93 kilometers east-northeast of Cape Yakataga, Alaska at the time that I'm recording this demo. So there's a bunch of earthquakes. We've gotten the data. But looking at a CSV file is not very interesting. Let's go ahead and create an image out of it. In order to do that, I will run transform.py. So transform.py is essentially getting the earthquake data, converting an image. And notice at this point, there's no image. But now if I do lsstar.png, I now have an earthquakes.png. So let's go ahead and now put it onto the cloud. We want to get rid of this virtual machine. The whole idea is compute and storage are separate. So we've done the compute. We have some files. Let's copy them off the machine into cloud storage so that we can delete the machine. Right? So let's go and create a cloud storage bucket. The way to do that is, again, go down here. And last time we did compute engine. This time we're going to do storage. So we'll go to storage browser and say that we want to create a bucket. Okay, so let's go ahead. I already created this bucket. Let me just delete that. I don't need that bucket. Let's say that I want to create a bucket, and I have to give my bucket a unique name. So let's say that I want to give the bucket the name earthquake, but the bucket name is already in use. A bucket name has to be globally unique. So I can say earthquake 2019, and I have it, right? So there is nobody else who's created a bucket of this name. If you can't come up with a unique name, try using a project name, right? This project name is also globally unique, and in many cases, that might work as well. An easy way to do that is we could go down to the home menu, and there is a project name. I can copy the project name, go back to the storage thing and say, can I create a bucket of that name? Yep, I can. So that also works. So I can create something with this particular name as my bucket. Let's make it multi-regional so we can access it from anywhere in the world. and it's going to cost us about 3 cents per gigabyte per month. And we can now choose how to set the permissions. Normally, you want to set permissions, but one object by object, right? But let's go ahead and specify it object by object. So we can go ahead and create the bucket. So now we've created a bucket with this name, and I'll copy that into my thing. And that bucket is now created. We can now come back to this virtual machine, and we can say gsutil ls and the name of the bucket. And it doesn't have anything in it right now. So it should be empty. So it doesn't have anything in it. What we can now do is we have gsutil copy earthquakes.star to the bucket. So at this point, it's copied 3 files. It's copied the CSV file, the HTML file, and the PNG file. And indeed, when we come down here and we say refresh, we should have the 3 files. So hooray. So we have the 3 files. All 3 files currently are not public. So no one can access them except us because we own these files. But from this point onwards, I don't need the virtual machine. So let me just go down to the compute engine and say, hey, that virtual VM instances, select my virtual machine, and I can do one of 2 things. I can stop the virtual machine, in which case it's like pausing the VM. I'll be paying for the disk, but I won't be paying for the storage at all, right? The other thing that I can do, instead of stopping the VM, is that I can delete the VM, right? So I can go ahead and delete the VM. I don't need it ever again. So stopping is actually a very convenient way. We've installed a bunch of software. We don't want to get rid of the VM, but we don't want to pay for the compute of the VM. So what we could do is we could just stop it, right? So the VM is no longer running, and we can just say stop. And now the VM is paused. And at this point, right, once that VM is paused, we'll only get charged for that 10 gigs of disk that we had attached to the VM. So a relatively inexpensive way to have a virtual machine sitting around that has all of the software, everything that we have installed on it. If we ever need to run things again, we can come back, restart the VM, and run things. But let's go back to our storage. Okay. And you will see that the data here is private. And what we want to do is that we want to make it public. We want to make it accessible from anybody. What we could do is we could go down to the storage. And now we are in the bucket. And we can say that we want to take these 3 files, go to the permissions, okay, right? And we can say that we want to go to the permissions and we want to add members. And we can add a members called all users, okay, and give those users, everybody, storage object viewer. So they will be able to view that particular object. Okay. So now we have our all users, okay, and all users has a storage object viewer on these objects. So now if we go now, we see that these 3 things are public, and Google Cloud helpfully warns us that these 3 things are public. They all have public links associated with them. So we can actually go down here and say, what is a public link? Click on the link, and that is storageapis.googleapis.com. So anybody who comes to this particular link will be able to basically see the earthquakes this week. So this is, at this point, I'm recording it on March 28th. I'm recording it on April 4th. So the week started on March 28th. So I have 7 days of data. And these are the earthquakes that we saw in Alaska. And those are the earthquakes that we saw in California. And you can kind of see the ring of fire with all of these earthquakes that are happening around the coast of the Pacific. But to bottom line, what did we do? We spun up a virtual machine. we carried out processing on it, and then we took those files, we copied them to cloud storage. We were able to stop the VM. VM is no longer running, but the files are still available, and we're able to serve them out. In the demo at the end of the previous section, I copied the ingested and transformed files out of the compute instance into cloud storage. This way, we could stop our compute instance and retain access to the data. While we've discussed the demand for a great amount of computing power for today's big data and ML jobs, we still need a place to store all the data that's generated. As with the demo, this needs to be separate from the compute instances so that we can analyze it, transform it, and feed it into our models. This is one major way that cloud computing differs from desktop computing. Compute and storage are independent. You don't want to think of disks attached to the compute instance as the limit of how much data you can process and store. Getting your data into your solution and transforming it for your purposes should be your first priority. In the roles and team structure discussions that I'll talk about later in this module, I'll talk about the need for data engineers to build data pipelines before you can start building machine learning models from that data. And when the pipeline is built, the job isn't done. Because once the data is in your system, data engineers are still needed to replicate the data, back it up, scale it, remove it as needed, all at scale. Instead of data engineers managing storage infrastructures themselves, data engineers can use Google Cloud Storage, which is a durable global file system. Creating an elastic storage bucket is as simple as using the web UI in console.cloud.google.com or the Google Storage Utility function called gsutil in the command line interface. As an additional level of flexibility, a data engineer can choose what type of storage class they want for their data.
There are 4 storage classes for you to choose from based on your data needs: standard storage, nearline storage, cold line storage, and archive storage. Regardless of which one you choose, all classes have multi-region, dual region, and region location options. So they differ based on the access speed and the cost. Standard storage is the fastest, and archive storage is the least expensive. A good trade-off, for example, is to use nearline storage for data that you might access only monthly. For data analysis workloads, it's common to use a standard storage bucket within a region for staging your data. Why do I say within a region? That's because you need the data to be available to your data processing computing resources. And these will often be within a single region. Co-locating your resources this way maximizes the performance for data-intensive computations and can reduce network charges. Cloud storage buckets are an example of a cloud resource. Let's cover some of the account management logistics that you need in order to use cloud resources.
Starting from the most granular objects, you see that resources, like your cloud storage bucket or compute engine instance, these resources belong to specific projects. Bucket names have to be globally unique, and GCP assigns you a project ID that's globally unique too. And so you can use that project ID as a unique name for your bucket. But what's a project? A project is a base level organizing entity for creating and using resources and services, for managing billing, APIs, and permissions. Zones and regions physically organize the GCP resources you use, whereas projects logically organize them. Projects can be created, managed, deleted, even recovered from accidental deletions. Folders are another logical grouping you can have for collections of projects. Having an organization is required to use folders. But what's an organization? The organization is a root node of the entire GCP hierarchy. While it's not required, an organization is quite useful because it allows you to set policies that apply throughout your enterprise to all the projects and all the folders that are created in your enterprise. Cloud Identity and Access Management, also called IAM or IAM, lets you fine-tune access control to all the GCP resources you use. You define IAM policies that control user access to resources. Remember, if you want to use folders, you must have an organization. Now that you have a Google Cloud Storage bucket created, how do you get your data on the cloud and work with the data once it's there in the bucket? In the demo, I used gsutil commands. Specifically, we can use cp for copy and specify a target bucket location. If you spin up a Compute Engine instance, the command line tool gsutil is already available and we can do gsutil copy. On your laptop, you can download the Google Cloud SDK so that you can get gsutil. gsutil uses a familiar Unix command line syntax, so if you know how to use the cp command on Unix, you know how to use gsutil cp. So far, we've looked at compute and we've looked at storage. The third part of Google Cloud infrastructure is networking. Google's high-quality private network, petabit bisectional bandwidth, and edge points of presence are combined using state-of-the-art software-defined networking to deliver a powerful solution. First, the private network. Google has laid thousands of miles of fiber optic cable that crosses oceans with repeaters to amplify optical signals. And as you can see in this amusing GIF, it's shark-proof. Google's data centers around the world are interconnected by this private Google network, which by some publicly available estimates carries as much as 40% of the world's internet traffic every day. This is the largest network of its kind on Earth, and it continues to grow. Second, the petabit bisectional bandwidth. One of the themes we will discuss in this course is a separation of compute and storage. You no longer need to do everything on a single machine or even a single cluster of machines with their own dedicated storage. Why? Well, if you have a fast enough network, you can perform computations on data located elsewhere, like many distributed servers. Google's Jupyter network can deliver enough bandwidth to allow 100,000 machines to communicate amongst each other. So for any machine to communicate with any other machine in the data center at over 10 gigabits per second. This full duplex bandwidth means that locality within the cluster is not important. If every machine can talk to every other machine at 10 Gbps, racks don't matter for data analytics and machine learning. But you need to ingest data, probably from around the world. You need to serve out the results of your analytics and predictions, perhaps to users who are all around the world. This is where edge points of presence come in. The network, Google's network, interconnects with the public internet at more than 90 internet exchanges and more than 100 points of presence worldwide. When an internet user sends traffic to a Google resource, Google responds to the user's request from an edge network location that will provide the lowest delay or latency. Google's edge caching network places content close to end users to minimize latency. Your applications in GCP, like your machine learning models, can take advantage of this edge network too. The last piece of core infrastructure underpinning your data pipelines and machine learning models is Google-grade security. When you build an application on your on-premises infrastructure, you're responsible for the entire stack's security, from the physical security of the hardware and the premises in which they are housed, through the encryption of the data on disk, the integrity of your network, and all the way up to securing the content stored in those applications. But when you move an application to GCP, Google handles many of the lower layers of security, like the physical security of the hardware and its premises, the encryption of data on disk, and the integrity of the physical network. Because of its scale, Google can deliver a higher level of security at these layers than most customers could afford to on their own. The upper layers of the security stack, including the securing of data, remain your responsibility. But even here, Google provides tools like Cloud IAM to help you implement the policies that you define at these layers. Communications over the internet to our public cloud services are encrypted in transit. Google's network and infrastructure have multiple layers of protection to defend our customers against denial of service attacks. Stored data is automatically encrypted at rest and distributed for availability and reliability. This helps guard against unauthorized access and service interruptions. One specific product I'll highlight here that you will see a lot of in this course is BigQuery, Google Cloud's petabyte-scale analytics data warehouse. Data in a BigQuery table is encrypted using a data encryption key. Then, those data encryption keys are themselves encrypted with key encryption keys. This is known as envelope encryption, and it provides additional security. BigQuery also allows you to provide your own encryption keys. These are called customer-managed encryption keys. Inside BigQuery, you can monitor your team's BigQuery usage and running queries and proactively limit access to data at a row and a column level. We'll cover BigQuery as a service in greater detail later. But in this section, we just wanted to point out BigQuery's security controls as an example of the kind of security controls that you will find in every service on GCP. So far, we've talked about low-level infrastructure, compute, storage, networking, and security. However, as a data engineer or data scientist or data analyst, you will typically work with higher level products. So let's talk about the big data and machine learning products that form Google Cloud Platform. We'll talk about the chronology of innovation, not for history's sake, but so that you understand the evolution of data processing frameworks. Knowing how these frameworks have evolved can help you understand the typical problems that arise and how they're addressed. One of the interesting things about Google is that historically, we have faced issues related to large data sets, fast-changing data, and varied data, what is commonly called big data, earlier than the rest of the industry. Having to index the World Wide Web will do that. And so, as the internet grew, Google invented new data processing methods. In 2002, Google created GFS, or the Google File System, to handle sharding and storing petabytes of data at scale. GFS is the foundation for cloud storage and also for what would become BigQuery managed storage. One of Google's next challenges was to figure out how to index the exploding volume of content on the web. To solve this, in 2004, Google invented a new style of data processing known as MapReduce to manage large-scale data processing across large clusters of commodity servers. MapReduce programs are automatically parallelized and executed on a large cluster of these commodity machines. A year after Google published a white paper describing the MapReduce framework, Doug Cutting and Mike Caffarella created Apache Hadoop. Hadoop has moved far beyond its beginnings in web indexing and is now used in many industries for huge varieties of tasks that all share the common theme of volume, velocity, and variety of structured and unstructured data. As Google's needs grew, we faced the problem of recording and retrieving millions of streaming user actions with high throughput. That became Cloud Bigtable, which was an inspiration behind HBase or MongoDB. One issue with MapReduce is that developers have to write code to manage all of the infrastructure of commodity servers. Developers couldn't just focus on their application logic. So, between 2008 and 2010, Google started to move away from MapReduce to process and query large datasets. And instead, they started moving towards new tools like Dremel. Dremel took a new approach to big data processing, where Dremel breaks data into small chunks called shards and compresses them into a columnar format across distributed storage. It then uses a query optimizer to farm out tasks between the many shards of data and the Google data centers full of commodity hardware to process the query in parallel and deliver the results. The big leap forward here was that the service auto-manages data imbalances and communications between workers and auto-scales to meet different query demands. And as you will soon see, Dremel became the query engine behind BigQuery. Google continued to innovate to solve its big data and ML challenges and created Colossus as a next-generation distributed data store, Spanner as a planet-scale relational database, Flume and Millwheel for data pipelines, PubSub for messaging, TensorFlow for machine learning, plus the specialized TPU hardware we saw earlier and AutoML that's going to come later. The good news for you is that Google has opened up these innovations as products and services for you to leverage as part of the Google Cloud Platform. You will practice working with these products in your labs as part of this fundamentals course.
Hello and welcome. I'm Philip Meyer, a course developer with Google Cloud Platform, and this is a brief tutorial on using QuickLabs in this course. You're about to use the interactive hands-on labs platform called QuickLabs, which is part of Google Cloud. QuickLabs allows you to get practical hands-on experience with GCP and provisions you with Google account credentials so you can access the GCP console at no cost. Once you reach the lab item in this course, click the Open button. You will then be prompted to provide the email that you want to use for your QuickLabs account. If you already have a QuickLabs account, you can use that email and then log in with your QuickLabs password. If you don't have a QuickLabs account, a new one will be created for you with the email that you provide. Once you're in QuickLabs, click the Start Lab button and wait until lab running is displayed. For each lab, you will have a timer with the remaining access time. You can see that right up here, and your lab will automatically end when the timer runs out. To get started, you want to click the Open Google Console button, and you're going to want to sign in with the username and password that are provided in this pane over here. So let me copy the username, Click Open Google Console. I'm going to paste in that username. I'm going to go back and grab the password. I'm going to paste that in as well. And Qwiklabs creates a new account for you each time you launch a lab. Therefore, you're going to have to click through some initial account setup windows. So in this case, I'm going to accept this over here. I don't need to do anything here. I can just click Done. And then once I'm in the GCP console, I can verify that I'm using the Qwiklabs provided account and project. I first need to also agree to the terms of service. I click Agree and Continue. And then over here within the dashboard, I can see the project name, the project ID, the project number. I can also see the project ID up here. And I want to make sure that these are the same and that they match the connection details that we have in the Qwiklabs page. So let me go and verify that this here corresponds to the project ID over here. And we can see it's just cut off slightly there. There we go. So indeed, we are using the right project. And we can also verify that we're using the right username. You can click on this icon up here. We can see we're not logged in with our own account, but with the Qwiklabs provided account. And this is very crucial. So let's also verify that this corresponds to the username that we are provided over here. Okay. Now, some labs track your work within the Qwiklabs provided GCP projects. And if this is enabled, you'll see a score in the top right corner of the Qwiklabs window, as you can see right here. And your score increases as each of these objectives here are met. And you can click on the score to view, as you can see here, the individual steps. So let me go ahead and complete these activities to show you what that looks like. Now that I have completed the lab, I can see that my score has been updated and I'm ready to click End Lab. And once I click End Lab and confirm so, the Qwiklabs provided project and any resources within that project will be deleted, and I can continue learning in Pluralsight. That's it for this tutorial. Remember to use the Qwiklabs provided credentials to sign into the GCP console. Good luck with the labs and enjoy the rest of this course.
choosing which big data and machine learning products are the right mix for your solution is a critical skill that you have to learn. Later on in this module, you will get the opportunity to examine the architecture that real Google Cloud customers use so that they can serve as inspiration. Let's review the options available to you for compute and storage services so that you can better interpret those use cases later. The service that might be the most familiar to newcomers is Compute Engine, which lets you run virtual machines on demand in the cloud. It's Google Cloud's Infrastructure as a Service, or IaaS, solution. It provides maximum flexibility for people who prefer to manage server instances themselves. GKE, Google Kubernetes Engine, is different. Where Compute Engine is about individual machines running native code, GKE is about clusters of machines running containers. Containers have code packaged up with all its dependencies. So GKE enables you to run containerized applications in a cloud environment that Google manages for you under your administrative control. Containerization is a way to package code that's designed to be highly portable and to use resources very efficiently. Since most use cases involve multiple programs that need to execute and communicate with each other, you need a way to orchestrate the containers running these separate programs. That's what Kubernetes does. Kubernetes is a way to orchestrate code that's running in containers. Although Kubernetes and GKE are outside the scope of this course, I'll link to our cloud architecture specializations in the course resources. App Engine is GCP's fully managed Platform as a Service, or PaaS, framework. That means it's a way to run code in the cloud without having to worry about infrastructure. You just focus on your code and let Google deal with all the provisioning and resource management. You can learn a lot more about App Engine in the specialization Developing Applications in Google Cloud Platform. Cloud Functions is a completely serverless execution environment, or Functions as a Service, FaaS. It executes your code in response to events, whether those events occur once a day or many times a second. Google scales resources as required, but you only pay for the service while your code runs. So what's the difference between App Engine and Cloud Functions? Typically, App Engine is used for long-lived web applications that can auto-scale to millions to billions of users. Cloud Functions are used for code that's triggered by an event, such as a new file hitting cloud storage. The fastest way to lift and shift your data workloads is by provisioning a VM and running your code. You'll experiment with this later on when you run Spark ML jobs on Cloud Dataproc, which spins up Compute Engine instances for your cluster. Most applications need a database of some kind. If you've built a cloud application, you can install and run your own database for it on a virtual machine in Compute Engine. You simply start up the virtual machine, install your database engine, and set it up, just like in a data center. Alternatively, you can use Google's fully managed database and storage services. What all these, Bigtable, Cloud Storage, Cloud SQL, Spanner, Datastore, what all these have in common is that they reduce the work it takes to store different kinds of data. GCP offers relational and non-relational databases and worldwide object storage. You will learn more about these later on in this course. GCP also offers fully managed big data and machine learning services. Just as with storage and database services, you could build and implement these services yourself, but why manage the infrastructure for compute and storage when it can be fully managed by Google Cloud? Here's a complete list of big data and ML products organized by where you would likely find them in a typical data processing workload. On the left, you will see the foundation to where your raw data is stored. If your data isn't stored on GCP yet, you can ingest it using the tools that you see next. After your data is on GCP, you can analyze it using the tools in the third column and run machine learning on it with the tools in the fourth column. The last column is how you can serve out your data and ML insights out to your users. Now it's time to explore some cool big data and machine learning solutions that have been built using Google Cloud. Then you will get a chance to find a use case and explore it in your own activity. Keller Williams is a US real estate company. Keller Williams uses AutoML Vision to automatically recognize specific features of houses, like this house has a built-in bookcase. This helps agents get houses listed faster and buyers find houses that meet their needs. Neil Dolakia, Chief Product Officer of Keller Williams, says that by training a custom machine learning model to recognize common elements of furnishings and architecture, customers can automatically search home listing photos for specific features like granite countertops, or even more general styles like show me modern houses. This application of machine learning allows Keller Williams realtors to quickly walk around a home and record a video and use the object detection capabilities of AutoML Vision to find and tag key aspects of the home that customers might want to search on. A big benefit for their organization is that they already had many existing images and videos of home walkthroughs already. They simply fed them into the pre-built AutoML Vision model and customized it, all without writing a line of code. You will learn more about AutoML Vision and practice creating machine learning models with it later in this course. Ocado, the UK online-only grocery supermarket, used machine learning to automatically route emails to the department that needed to actually handle them. This avoids multiple rounds of reading and triaging those emails. With their old process, all the mails went to a central mailbox where the email was read and then routed to the person or department that could handle it. Unfortunately, the central mailbox with somebody reading all the emails, that doesn't scale. And so it led to long delays and poor user experience. So Ocado used machine learning, specifically the ability to read an email, to process natural language, to discover customer sentiment and what the message was about so that they could route it immediately and automatically. One last use case. Kewpie manufactures baby food. In this case, quality is not necessarily a matter of safety because the food itself is safe. But if baby food is discolored, it tends to get parents very concerned. So Kewpie turned to Google and our partner BrainPad to build a solution that leverages image recognition to detect low quality or discolored potato cubes. The machine learning algorithm enabled them to free people up from the tiring work of inspection and focused on other more important work. Now it's your turn. One of the best ways to inspire and drive your team and projects to the cloud is to show your stakeholders examples from your industry, examples where someone has already succeeded with building a solution. For this activity, navigate to cloud.google.com/customers and scroll down. For products and solutions, filter on big data analytics and also on machine learning. Select a customer use case that interests you. Then answer these 3 questions. Number 1, what were the barriers or challenges the customer faced? The challenges are important. You want to understand what they were. Second, how were these challenges solved with a cloud solution? What products did they use? And 3, what was the business impact? Take a moment to complete the activity and then return to the video. For our example, we chose Gojek because they use a data engineering solution that maps nicely to the topics that we're going to cover as part of this course. Gojek is an Indonesia-based company that gives shared motorcycle rides, brings goods, and provides a wide variety of other services for over 2 million families across 50 cities in Indonesia. Their app has over 77 million downloads, and they're connected with over 150,000 merchants who sell through their delivery platform. And if you're interested in GIS data, they have over 1 million drivers delivering goods and giving rides across 50 cities, and Gojek gets sensor data from all of these drivers. So Gojek manages more than 5 terabytes per day of data for analysis. The Chief Technology Officer, the CTO, Ajay Gore, gives this meaningful statistic. For example, we ping every one of our drivers every 10 seconds, which means 6 million pings per minute and 8 billion pings per day. That's Gore who's saying this. If you look at the scale and number of our customer interactions as well, we generate about 4 terabytes to 5 terabytes of data every day. We need to leverage this data to tell our drivers where demand from customers is strongest and how to get there. With the success of their on-demand motorcycle ride service, Gojek faced the challenges when looking to scale their existing big data platform. What challenges? Their management team stated, most of the reports are produced 1 day later, so we couldn't identify the problems that were happening as soon as possible. Gojek chose Google Cloud Platform and migrated their data pipelines to GCP so that they could get high performance with minimal day-to-day maintenance. Their data engineering team uses Cloud Dataflow for stream data processing and Google BigQuery for real-time business insights. Their end-to-end architecture looks like this. First, they ingest data from their mobile app, online, and IoT devices on vehicles, like the GPS tracking for deliveries. They ingest this data into Cloud PubSub. Then, the data is brought into Cloud Dataflow for processing, and a variety of other data sources are used to enrich this event data. Finally, after Dataflow has done the processing, Dataflow streams the data into BigQuery, and BigQuery in this case is used as a data warehouse to store the data. What's the business impact? So here's an example of one of the problems that the Gojek team solved. The question was, how could they quickly know which locations had too many drivers or too few drivers? Too few drivers to meet the demand for that area. To solve this problem, what does the team need to do? Number one, they needed to check the demand of bookings by customer against the supply of drivers and do this thing in real time. Then the team needed to identify who these drivers are and notify them to reroute to higher demand areas. How they achieved this was by building a streaming event data pipeline using Cloud Dataflow. Driver locations would ping out to PubSub every 30 seconds, and these locations would go into Dataflow for processing. The Dataflow pipeline aggregates the supply pings from the drivers against the request for bookings and then connects to Gojek's notification system to alert drivers. From a technology standpoint, the system needs to handle an arbitrarily high throughput of messages and scale up and down to process. Cloud Dataflow automatically manages a number of workers processing the pipeline to meet demand. The Gojek team is then able to visualize and highlight supply-demand mismatch areas for management reporting, as you see in this example here. The green dots, the small green dots, represent riders and new booking requests. And the red dots, the small red dots, those are the drivers. So you have the riders in the green dots and the drivers in the small red dots. And then you see the areas that the system has identified as the highest mismatches of supply and demand. Those areas are highlighted in red, like the train station, which has many booking requests, but not enough drivers. The team can now actively monitor and ensure that they're sending drivers to the areas in highest demand, which means faster booking times for riders and more fares for the drivers. So far, you've seen the infrastructure, the software, and the customers who are already using GCP. But the most critical factor to the success of your future big data and ML projects is your team itself. The people and the core skill sets required will make or break your next innovation. A common mistake that companies make is that they go out and hire 10 PhD machine learning scientists and expect magic to happen. I see this a lot with companies who are new to building data science and ML teams. They focus on the ML researchers and forget about all the help and guidance that the ML researchers will need. The reality, as my colleague Cassie has noted in a blog post, looks more like this. You need data engineers to build the pipelines and get you clean data, decision makers to decide how deep you want to invest in a data-driven opportunity while weighing the benefits for the organization, analysts to explore the data for insights and potential relationships that could be useful as features in a machine learning model, statisticians to help make your data-inspired decisions become true data-driven decisions with their added rigor, applied machine learning engineers who have real-world experience building production machine learning models from the latest and best information and research by the researchers, data scientists who have the mastery over analysis, statistics, and machine learning, analytics managers to lead the team, social scientists and ethicists to ensure that the quantitative impact is there for your project and it's the right thing to do. As I've written in a blog post on the subject, it's linked below, a single person might have a combination of these roles, but this depends on the size of your organization. Your team size is one of the biggest drivers in whether you should hire for a specific skill set, upskill from within, or combine the two. Do you remember these big data challenges? Can you see how different roles would map to these? Within Google Cloud Training, my team and I have thought about the different types of data science teams and roles that are using Google Cloud so that we can best tailor our data and ML courses and labs. One of the core challenges we face is how different types of users engage with our GCP big data and AI products. We'll be using a few personas in this course. Their backgrounds, goals, and challenges might be similar to yours. Let's meet them now, and you'll see them again later. Brittany and Theo lead their data engineering team in managing their Hadoop cluster for the organization's data pipelines and compute jobs. Their organization was an early adopter of Hadoop for distributed computing back in 2007, and they've built up Hadoop jobs over time. And Brittany and Theo's job is to actively ensure that the Hadoop jobs are all run and that the cluster is well maintained. They say, our CTO has challenged our data engineering team to find ways we can spend less on managing our on-prem cluster. Right now, we just want to show her options that don't require any code changes to our 100 plus Hadoop jobs. Brittany and Theo are data engineers who manage your company's data platform and are focused on reducing maintenance burden. Jacob is a data analyst who has a background in building and querying his company's MySQL transactional and reporting database. As the company grows, the reporting tables in his RDBMS are already starting to slow down, and users are reporting long query and dashboard loading times. He wants to find an easy path for scaling his company's data reporting and not have to manage another data system as the data needs grow. Jacob is a data analyst who wants to be able to derive insights from data and disseminate them with as little friction as possible. Rebecca is a data engineer whose company specializes in harnessing data from the Internet of Things or IoT devices. She says, I really want to design our data pipelines for the future. For us, that means lots and lots of streaming data from our IoT devices with low latency. Her team lead has asked her to come up with a plan to handle the expected 10x growth in streaming data volumes this year. She wants to future-proof her team's pipelines, but doesn't want to spend hours manually scaling hardware up and down as streaming volume changes. Additionally, her business stakeholder team wants insights from all the IoT devices in the field on their dashboards with minimal delay. Vishal says, I pitched my team on the value machine learning can add, and I've got buy-in to build a prototype. But now I've got to build a prototype. What are some of the easiest ways I can see whether machine learning is feasible for my data? Vishal is an applied machine learning engineer who has a background in building machine learning models in TensorFlow and Keras. His team is growing rapidly, and he's often asked by his leadership to assess the feasibility of machine learning for a wide variety of projects. He doesn't have the time to train and test all of the ideas with custom models, and he wants to empower his data analyst and data engineering teams by teaching them machine learning. Do these personas sound familiar to your role and your team? Next, we learn more about the Google Cloud Platform, big data and machine learning approaches and solutions so that we can address each of these challenges. Hi, I'm Lak. Welcome to the third module of our Big Data and Machine Learning Fundamentals course. This module is on performing product recommendations using Cloud SQL and Apache Spark. We'll cover product recommendations, which is probably the most common machine learning problem employed by businesses. Along the way, we'll also get to look at two Google Cloud products, Cloud SQL, which is a managed relational database, and Cloud Dataproc, which is a managed environment on which you can run Apache Spark. Managed? What's managed? Stick around. We'll start out talking about recommendation systems, what they are, what business applications they power, and consider a typical scenario. In this case, that is product recommendations using machine learning for recommending rental houses. Let's say that our data science team is familiar with Hadoop and Spark, and they've already built a recommendation system. Our mission, which we have chosen to accept, is to migrate this existing recommendation system that our team has built from on-premises cluster to the cloud. We'll look at how you would go about migrating on-premises applications to Google Cloud Platform. In particular, why you would want to migrate an on-premise application to Google Cloud Platform. Maybe it is to avoid the challenges that are associated with utilizing and tuning on-premise clusters. But also, when you move an on-premise application to Google Cloud, you're also moving from dedicated storage to off-cluster storage with Google Cloud Storage. And we'll talk about why that is. Let's start with where you find recommendation systems adding value to businesses. Where have you seen recommendation systems before? One common place that comes to mind is e-commerce product recommendations. A model learns what you like and don't like, what you buy and don't buy, and then starts to suggest similar products that you may not have discovered by yourself. You can then help inform the model explicitly by starring, upvoting, or downvoting your own personal rating of an item, or maybe by adding the item to the shopping cart. Notice how I said explicitly. A model can learn from your preferences implicitly too. Can you think of a few data points that an e-commerce model could learn without you explicitly rating items? Perhaps time spent on the website of particular products. Maybe items that you have last viewed. Maybe where you navigated from, what device you are on, and if you've allowed it, geographic personalization as well. Things that people who live in your neighborhood or your country tend to buy. You have probably seen recommendation engines in Netflix, Amazon, and so on. It's also what Facebook uses to put posts on your newsfeed and what Google uses to personalize your search results. Product recommendations are the first machine learning application that the public recognizes. As in, how does Netflix know that I will like this movie? The general population was pretty unaware of machine learning applications like medical diagnosis, or airline fares, or detecting illegal logging, or playing chess, until it got to product recommendations, where if you like X, you will also like Y. And that tuned the public in to the idea of machine learning. One cool example of a recommendation system is Smart Reply in Gmail. This is the machine learning model that recommends 3 possible answers to your emails. Another is how Google Photos recommends similar photos or groups of similar photos so that you can add them into an album and you can order a printed version of it. Another example is how Google Maps now serves personalized restaurant recommendations. When you explore a new area, the app provides users with a For You tab, which lists restaurants and venues that it thinks you will enjoy based on your history. For example, here you can see that Good Barbecue is a 95% match for me, as well as a recommendation for a new bistro that is trending. A core aspect of a recommendation system is that you need to train and serve it at scale. Think of the machine learning system that drives YouTube recommendations for users. It identifies things that a user may like based on what they've watched in the past and serves them these video recommendations, like these video recommendations that I got when I logged into YouTube. Most of the recommendations here are about programming, TensorFlow, or machine learning, which I guess says a lot about the videos that I like. These recommendations are relevant and useful to me. In the following lessons, you'll implement your own recommendation system for housing rentals. Now that you've seen how recommendation systems are used at Google and in other businesses, it's time to look into the specific scenario that we'll use in the next lab. The core pieces of a recommendation system are data, the model, and infrastructure to train and serve recommendations to users. Our data set for this scenario will be housing rentals that we want to recommend to our users based on their preferences. We'll use a machine learning model to make these recommendations. A core tenet of machine learning is to let the model learn for itself what the relationship is between the data that you have, like user preferences and housing features, and the data that you don't have, like a user's rating on a property that they haven't yet seen. What would this user rate this property if we showed it to them? You will not be writing custom logic like, if the house is a beach house and the season is summer and the user likes cozy houses, then house number 22 is what we recommend. Can you think of the issues if we used such logic instead of letting the model figure it out? What if there were many different kinds of beach houses with all kinds of different features, like the number of bedrooms, locations, amenities? You get the picture. What if you have different kinds of users? Some users who like to go to beach houses in summer and others who like the shoulder season. Hard coding logic for all these features and different kinds of user segments isn't scalable, and it assumes that we always know the right answer for every scenario. Let's illustrate this point with an example. Take Google search. Say you go to Google and search for giants. What should we show you as the results to make it most relevant for you? If you're in California, should we show results for the San Francisco baseball team and the local games nearby? What about if you're based in New York? Should we tailor the results to show the New York Giants football team instead? And should we write this as a rule? Well, up until a few years ago, this is exactly how Google search worked. There were tons of rules that were part of the search engine code base to decide which sports team to show a user when they search for Giants. If the query is Giants and the user is in the Bay Area, show them results about San Francisco Giants. If the user is in the New York area, show them results about New York Giants. If they're anywhere else, show them results about tall people. Just imagine how many if-then or case statements this would be and how hard it would be to maintain. And this is just for one query. Multiply this by the large variety of queries that people make, where they make them from, what device they're on, and what kinds of interests different people have, and you can imagine how complex the code base would become. The code base starts to get unwieldy because hand-coded rules are really hard to maintain. So this is where machine learning comes into play. Machine learning scales much better because it doesn't require hard-coded rules. It's all automated, learning from data in an automated way. That's what machine learning is. Our data set in this case is that we know historically when people searched for giants and we showed them a bunch of links, which of those links did people click on? Since we know this, we have a data set of a query term and the links that people liked. Why can't we train a machine learning model to basically provide a ranking of these links? And that's exactly what Google itself did internally with a deep learning model called RankBrain. After rolling it out, the quality of our search ranking results improved dramatically, with the signal from RankBrain becoming one of the top 3 for influencing how different link results are ranked. If you're interested, I'll provide a link where you can read more about it. We'll revisit machine learning in greater depth in each of the modules in this course. But for now, just remember that machine learning is this idea that we want to teach the computer using examples, not with rules. Any business application where you have those long switch or case statements or if-then logic manually coded, and you have a history of good labeled data. That is data for which you know a good answer or a bad answer, right? A history of good labeled data. Any such application is a possible application for machine learning. So how would housing recommendations work in our system? First, we need to ingest the ratings of all the houses that have already been done by our users when we showed them specific houses. So we have to go to our inventory of rentals and ingest the ratings for the houses. These ratings could come from explicit ratings. Maybe we showed the user the house in the past and they clicked 4 stars after seeing the house details. Or the ratings should come from implicit ratings. Maybe they spent a lot of time looking at the website corresponding to this property. Then we'll train a machine learning model to predict a user's rating of every house that we currently have in our listing database. We will then pick the top 5 rated houses that they haven't already seen. People who are not aware of recommendation engines somehow think of a car appearing on their Facebook feed because they happen to read an automobile review article. They say, oh, I was reading this review article and then just kept seeing cars in my Facebook feed. That's not the case. Reading the article caused the rating of all cars to go up, and the ratings of other items that are not cars to stay relatively the same. And this caused the highest ranking car to get into the top 5. So there was always a rating for the car. The car was always there, but its rating was simply lower before they read the article in question. So how would we predict a user's rating of a house, particularly if they haven't seen it before? The model is based on 2 things. It's based on your other ratings. What have you rated other houses? And other people's rating of this particular house. A particularly simple model could be to look at all the users who rated this particular house and find the 3 users in their list who are most like you. Maybe they live in your country, maybe they have the same age, maybe they went to the same college. Find the 3 users in that list who are most like you. And then the prediction is the average of those 3 users' ratings. This is not a great model, of course. It's too easy to game. Think about what happens if 3 people gang up together and rate a house that nobody else cares about. So there are only 3 ratings for this house. So the 3 closest users are going to be these 3 people. So for sparse houses, it's really, really, really easy to game. But this idea of using user ratings of a particular house and users like you helps convey the basic premise of how recommendation models work. So where is the machine learning here? Where is the learning? The model would have to figure out how to find the users who are most like you. How many users to consider? 3 users, 5 users, 7 users, how many? And how to weight the different factors, such as the overall popularity of the items you have in common, and so on. This can be done by seeing what parameters help predict if you intentionally withheld ratings best. So we may have thousands of items and only 2 to 3 reviews per item. The chances are those reviewers have nothing in common with the user that we want the rating for. So, because this rating matrix is extremely sparse, we need to cluster items and users together. To put this in a more intuitive way, imagine that all of your friends drive SUVs, sport utility vehicles, and you read an article on Porsche. The car that appears on your feed might be a Porsche SUV, even if the article was on Porsche cars and all your friends drive Toyota SUVs. The machine learning model is imputing a rating for a Porsche SUV that is quite high, even though none of your friends rated it. So the machine learning model is essentially asking, who is this user like? And secondly, is this objectively a house that people tend to rate highly? The predicted rating is a combination of both these factors. All things considered, the rating of a house for a particular user will be the average of the ratings of users like this user, but it's calibrated by the quality of the item itself. Now that we understand the problem and the approach, we need to address the last question, the infrastructure question. How often and where will you compute the predicted ratings? And once you have them, once you've computed these ratings, where would you store them? What do you think? How often and where will you compute the predicted ratings? It's not as if rental recommendations have to be updated every time some user somewhere rates a house. We don't need to update the rental recommendations every time a new rating appears in our system. It's probably sufficient if we update the recommended houses for users once a day, maybe even once a week. In other words, this does not need to be streaming. It could be batch. On the other hand, we will probably have thousands of houses and millions of users. So it's probably best that we compute the rating that every user will give every house. We do that computation in a scalable way. We don't want to do it on a single machine. We want to do it in a fault-tolerant way that can scale to large data sets. So a typical solution for computation that has to happen over large data sets in a fault-tolerant way is to do it in a big data platform like Apache Hadoop. Finally, where will you store the computed ratings? Why would you want to store them? Well, we probably want to power a web application with these recommendations, and we don't want to compute recommendations when the user visits a web page. We want to pre-compute these recommendations. As we said, it's a batch job. So once a day, once a week, we pre-compute it. And then when the user logs on, we want to show that user the recommendations that we pre-computed specifically for them. So we need a transactional way to store the predictions. Why transactional? So that while the user is reading these predictions, we can update the predictions table as well. Assuming that there are 5 predictions for every user, and we have 1 million users, that's a table of just 5 million rows. It's small enough and compact enough that a typical solution for this would be to store the data in a relational database management system, an RDBMS like MySQL. So we decided to use a big data platform like Hadoop and an RDBMS like MySQL to solve the housing recommendations problem. These are both open source technologies. You probably have Hadoop clusters and MySQL database running on premises. So let's assume that your team already has this recommendation system working on-prem and see how to migrate it from on-premises to Google Cloud Platform. Of course, you want to do that only if the migration can add value. So we will look at that as well. For our housing recommendation model, let's say our data science team already has a working on-premise model using a Spark ML job on your Hadoop cluster. They're interested in the scale and flexibility of GCP, and they want to do a like-for-like migration of their existing Spark ML jobs from on-premises, and they want to do this as a pilot project. As explained in the previous lesson, we can get away with computing predicted ratings once a day. We don't need to compute recommendations in real time. So Hadoop batch processing is enough. Here, we'll use Spark ML, but instead of doing it on premises, we'll run the machine learning job on Cloud Dataproc and store the ratings in an RDBMS in Cloud SQL, because this is a relatively small data set of 5 recommendations for every user. So this is what you will practice in your first lab. Incidentally, this is why the smart reply in Gmail is so amazing. Unlike our housing recommendations, smart replies recommendations have to be done in real time when a new email pops up in your mailbox. Needless to say, Gmail is doing something far more sophisticated than what we're talking about here. Here is how we decided on using Cloud SQL among the other big data products available for storing our ratings. This is a good reference to follow based on your storage access pattern. We'll cover the solutions in your other scenarios in this course, but briefly, use cloud storage as a global file system. Use Cloud SQL as an RDBMS, as a relational database management system for transactional relational data that you access through SQL. Use Datastore as a transactional NoSQL object-oriented database. Use Bigtable for high throughput NoSQL append-only data. So not transactions, append-only data. So a typical use case for Bigtable is sensor data for connected devices, for example. Use BigQuery as a SQL data warehouse to power all your analytics needs. So here, we wanted a transactional database and we expect to have data volumes in the gigabytes or less, and so hence Cloud SQL. If you're a more visual learner, here is another good map of visualizing where to store your data in GCP. If your data is unstructured, like images or audio, use cloud storage. If your data is structured and you need transactions, use Cloud SQL or Cloud Data Store, depending on whether you want your access pattern to be SQL or NoSQL. And by NoSQL, we mean a key value pair. In other words, you'll be trying to search for data based on a single key, use Data Store. If you'll be finding data using SQL, use Cloud SQL. Cloud SQL generally plateaus out at a few gigabytes. So if you want a transactional database that is horizontally scalable, so that you can deal with data larger than a few gigabytes, or if you need multiple databases, so you want them spread globally, use Cloud Spanner. So another way to say it is, if one database is enough, use Cloud SQL. If you need multiple databases, either because you have a lot of data or because your application needs to be transactional across different continents, use Cloud Spanner. If your data is structured and you want analytics, consider either Bigtable or BigQuery. Use Bigtable if you need real-time, high-throughput applications. Use BigQuery if you want analytics over petabyte-scale datasets. For our housing recommendation use case, we want to store our ratings and predictions somewhere. This is a structured dataset of user ratings and houses. It's built for a transactional workload, writes and reads, and one database is enough for a small dataset, and hence we pick Cloud SQL. So what's Cloud SQL? It's a Google-hosted and managed relational database in the cloud. Cloud SQL supports two open source databases, MySQL and Postgres, and other database solutions. In our case, we'll be using MySQL. One of the advantages of Cloud SQL is that it's familiar. Cloud SQL supports most MySQL statements and functions, even stored procedures, triggers, and views. It brings the benefits of cloud economics in the form of flexible pricing. You can pay for what you use. What do I mean by that? GCP manages the MySQL instance for you. This means things like backup and replication. It's on the cloud, so you can connect to it from anywhere. You can assign it a static IP address, and you can use typical SQL connector libraries. Because it's behind the Google firewall, it's fast. You can place your Cloud SQL instance in the same region as your App Engine or Compute Engine applications and get great bandwidth. Also, you get Google security. Cloud SQL resides in secure Google data centers. So that covers where we'll be storing the recommendations. But how will we compute these recommendations in the first place? Where will we be doing the compute? Let's review where big data computations have been done historically and even today. Before 2006, big data meant big databases. Database design came from a time when storage was relatively cheap and processing was expensive, so it made sense to copy the data from its storage location to the processor to perform data processing, and then the result would be copied back to storage. Around 2006, distributed processing of big data became practical with Hadoop. The idea behind Hadoop is to create a cluster of computers and leverage distributed processing. HDFS, the Hadoop Distributed File System, stored the data on machines in the cluster, and MapReduce provided distributed processing of this data. A whole ecosystem of Hadoop-related software grew up around Hadoop, including Hive, Pig, and Spark. Around 2010, BigQuery was released, which was the first of many big data services developed by Google. Around 2015, Google launched Cloud Dataproc, which provides a managed service for creating Hadoop and Spark clusters and managing data processing workloads. The other piece of our system is a software that runs on Hadoop. The software in this case is to train a machine learning model for creating housing recommendations. In this case, we used SparkML, which is part of Apache Spark. Apache Spark is an open source software project that provides a high-performance analytics engine for processing batch and streaming data. Spark can be up to 100 times faster than equivalent Hadoop jobs because it leverages in-memory processing. Spark also provides a couple of abstractions for dealing with data, including what are called RDDs, or resilient distributed datasets and data frames. Okay. We'll be using our Spark job for the housing rental recommendations, but we'll be doing the computation on Cloud Dataproc.
One of the most common use cases is running your Apache Spark jobs on your Hadoop cluster. Now let's do a demo of creating a new cluster and running a Spark job using Cloud Dataproc. And our goal will be to do it in 10 minutes or less, which if you've ever seen an on-premises Hadoop cluster by yourself, that seems like a pretty big win for infrastructure setup time and efficiency. Let's get started. All right, here we are in the Google Cloud Platform console. This is Cloud Dataproc. How you get here is if you open up the navigation menu. I've got several favorites that I've pinned here, but I'll show you how to actually, if you scroll down in the products and services to big data, you see a lot of the products that we mentioned so far. Dataproc is right here. If you click that pin, that'll bring it all the way up here, which saves it, which is a nice little efficiency hack. Hovering over the Cloud Dataproc service, you'll see that you can click on clusters, jobs, or workflows. But if you just click on the logo, that'll take you to the clusters page. So here we have it. It is blank slate. So the first thing we wanted to do is create and provision an Apache Hadoop cluster on Dataproc. So the configuration details, as you might expect, are here. We'll give the cluster a great name. We're going to be estimating the digits of pi in a distributed fashion, so we'll just call it pi cluster. Here you can choose what type of availability, which is essentially the ratio of how many master nodes do you want to your n worker nodes. So we'll keep it standard. If you want to adjust the hardware, which is your compute, your CPUs, you can do that here. All the way down to, at the time of recording, having 160 virtual CPUs in ultra memory. We're going to keep just standard here. And 15 gigabytes of memory, 500 gigabytes of persistent disk, sure. These are all the settings. So if you're running a pilot project for an apples to apples comparison, just map your same infrastructure that you're using for your clusters. And the number of nodes we're going to maintain at just the 2 is there. And we'll go ahead and click create. While that cluster is spinning up behind the scenes, we'll go ahead and just fill out a job to start with. So I already ran a job previously, and you can tell that since I didn't have a cluster before, that I actually turned down that cluster. So we're going to be creating a brand new job. So click on submit job. You can keep the job ID, or we'll just call this estimate pi digits. Region global is fine. It's good that we have the cluster name, even though it's spinning up. It still has it here. You can submit a job and queue it to run. Job type, it's not a Hadoop job, it is a Spark job. You can see the different job types that you could select here. And now we need to find the Java class. This is SparkPy. I'll link the example, but you can actually see there's a bunch of other Spark examples that you can run. And it essentially just, it generates a ton of pairs of XY coordinates on a unit circle, or a circle with a diameter of 1, inside of a square, which is the Monte Carlo method for estimating the number of digits in pi. If you're interested, I'll link that there, but it's essentially we're running that and using the Hadoop worker nodes to process that in massive parallel. And the actual example where the jar file is, I'll just paste that in there from the example, And we are going to generate 1,000 of those XY pairs. That's just an argument that we're passing through. This is specific to the job that we're running. Don't always put 1,000 for your arguments unless your program requires it. And we'll go ahead and submit it. Now it's going to run. Let's see if that cluster is ready for use. Yes, we have the green check mark here. If we wanted to, you can actually click into the cluster and get a lot of really good monitoring metrics that you see here. From within there, you can see the jobs that are running. In this case, for the last 30 seconds, we've had this estimate pi digits job. Let's go ahead and monitor that job specifically. Naturally, you can have multiple jobs running on a cluster, multiple clusters running multiple jobs, and boom, we get the output of our job. We see that it started here, and if we scroll down far enough, it should give us a logged output. Boom, here we go. We're actually submitted the application, and we get the result, which is the pi estimation right here, and then the job is complete. Spark has been stopped. So now what you can do is we've got a successful job execution. It took 36 seconds, plus the time to spin up the cluster. Is the real power is you can go ahead and turn down that cluster now. Now, if you wanted to have a long-lived cluster because you had persistent data on there, sure, absolutely. We'll be talking a little bit about later about the separation of compute and storage to try to get out of using persistent disks on clusters and into using something like Google Cloud Storage. But if we don't need this cluster anymore, we're not trying to persist any data. We have already ran our calculation. It's just as simple as clicking the delete icon and bring that cluster down. Don't worry about managing the infrastructure. You've got what you needed from that particular job. Or if your job's done, you want to submit more jobs or rerun the same job here. Use however many clusters, whatever size of clusters, edit the resources on the fly. The big takeaway is that clusters are now what we call fungible resources. They're ephemeral. You use them when you need them to submit your jobs. If you need them longer, or if you need them shorter, if you need more clusters or fewer clusters, you can manage that infrastructure automatically here through Cloud Data Proc. That's in essence what it is. So my challenge to you is inside of your lab a little bit later when you're building the recommendation engine using Cloud SQL and Cloud Data Proc, experiment within Cloud Data Proc, take a look at the logs for each of your different running jobs. And if you're running on-premise workloads within Hadoop, see if you can experiment with running some of those jobs within Cloud Data Proc and see which one is more efficient.
We said we would talk about common big data challenges and how they're addressed. One of the most common challenges for managing on-premise Hadoop clusters is making sure they're efficiently utilized and tuned properly for all the workloads that their users throw at them. So let's check in with our team and see what challenges they are facing running the Spark ML job on their on-premise cluster. Our team has an on-premises data center running Hadoop represented by the blue box here. On any given week, they manage 4 different jobs for the organization. Our Spark ML recommendation job is one of the 4. The data is persisted in traditional HDFS disk-based storage. So here's an example scenario that might seem familiar to you. The team launches job number 1. Say for argument, it's a big data pipeline job, which ramps up and consumes 50% of the available on-premises cluster resources. Then, the team has a special request from marketing to run their prediction job for an upcoming campaign later today. That will be job number 2, and it ramps up and consumes the other 50% of available cluster resources. You probably see the problem now. If our Spark ML job was number 3 or number 4, it would get starved out of resources because the cluster's compute capacity is under-provisioned for the demands of the organization's Hadoop jobs. Or a costly alternative is where only one job is running and uses 50% of the cluster resources, and the other 50% of machines are powered and available, but they're not needed. The problem here lies in the static nature of the on-premise cluster capacity. The team needs a better way to optimize the usage of the cluster's resources without the headache of continually tuning and adding and removing servers themselves. This is where GCP can help. You can now think of clusters as flexible resources. With Cloud Dataproc, GCP's managed Hadoop product, you can spin up as many or as few cluster resources as your job needs in the cloud.